So let's say you've been put in charge of the next physics partay, and you don't want it to be just any sort of physics partay, you want it to be a physics dance partay. So you do some fundraising, and you raise some money, and you hire a DJ, and you get a caterer, and you get a dance hall, and everything's going real well. So the day the partay comes, and you open up the dance hall, and you start setting things up, and the caterer starts setting things up, and the DJ comes and starts setting things up, and then calamity strikes. See, the DJ brought 2 speakers for stereo sound because we need good stereo sound for our physics music, for the physics dancing at the physics partay. Now, I don't know what physics dancing looks like. It sounds kind of horrible, but in the end, the problem is that one of the speakers blows a fuse. And so now we're out of speaker. We only have 1 speaker, and we want good stereo sound for our physics dancing and the physics partay, but luckily we got a room full of physics students. And so we can use our physics knowledge to make the sound from 1 speaker seem like it's coming from 2 locations. So I want you to pause the video and think, what defining properties of waves could you use to make the sound from 1 speaker seem like it's coming from 2 different locations? Now, some of you may have said maybe reflection might work, and maybe it would, but there's probably a better way of doing this. Maybe you want to consider some diffraction. Let's review. Diffraction is when a wave goes through an opening and spreads out on the other side. So someone gets the bright idea to put the speaker outside the dance hall, which really isn't very good for the actual quality of the sound, but here's what they decided to do. So they put the speaker outside and they open up 2 windows. This way the sound can go through the 2 openings and diffract. So if you want to picture this, the sound does this, goes through the 2 openings and spreads out on the other side. And so the picture would look something like this. The sound diffracting through both of those openings, and then the sound waves are overlapping with each other. Now, wait a second, if the sound waves are overlapping with each other, what other property of waves will be exhibited by this? Yeah, it's going to be some interference, which means we're going to hear different things at different locations inside the dance hall. So in our diagram, let's say that each solid line represents the crest of a wave, and each dashed line represents the trough of a wave. So let's identify different points and see what sort of interference would occur. Let's say we're standing right here where the crest from this window is overlapping the crest from this window. If this were a wave on a string, it might look like this. Crest approaching crest. So what sort of interference occurs when a crest overlaps a crest? Yeah, that's going to be constructive interference. The amplitude is going to get larger. So in terms of a sound wave, what would you hear different about it if the amplitude is larger? It's going to be a louder sound. A larger amplitude is a louder sound, a larger vibration of the air particles. Okay, so I'll put this as a capital C there for constructive. And anywhere where crest overlaps crest, in fact, this line right down the middle, you're going to hear a louder sound. You're going to experience constructive interference. Well, what if we're over here? Here, we're at a trough is overlapping a trough. If these were waves on a string, it would look something like this. The troughs approaching each other. So what sort of interference would you get when a trough overlaps a trough? Well, that's going to be constructive as well. It's just the amplitude gets larger the other way. So what's going to be different about the sound? It's still going to be louder because it's still a larger amplitude wave. And so I'll put a C here, and here, and here, and anywhere right down the middle, you're going to hear constructive interference. It's going to be a little bit of a louder sound. But what if instead you're standing here? See, here is where the crest from this window is overlapping the trough from that one. On a string, that would look like this. What sort of interference do you get when a crest overlaps a trough? Well, that's going to be destructive interference. So what would be different about the sound there? It's going to be a smaller amplitude. It's going to be softer. They're either completely destroying each other or possibly partially destroying each other for a smaller amplitude. So I'll put a D there for destructive. And then over here, that's a crest overlapping a trough. That's going to be destructive as well. So what would this location be here? That's a trough overlapping a trough. Would that be constructive or destructive? Sure, that's going to be constructive. What about this point over here? That's a trough overlapping a crest. That's going to be destructive. This point over here is trough and trough. That's constructive. And this point over here is trough and crest. That's destructive. Okay, This is a fun game, but the reason why I did these particular points is when you were doing the fundraising for the physics partay, you didn't get a whole lot of money because honestly, who was going to contribute to a physics dance partay? So you got a really good deal on the hall because it's a very narrow hall. In fact, the back wall of the hall is here. Doesn't offer a whole lot of room for our physics dancing. And that's where the caterer decided to set up the buffet line. So let's consider what would you hear happen to the sound if you were to walk along here. So let's say here's the long buffet table, and over here is where you pick up your physics plates and cups and napkins, and your physics drinks, and your physics salad, and your physics entree, and your physics desserts. What would you hear happen to the sound as you walked in a straight line across? Well, because of the interference, it would go in and out. It would be softer, louder, softer, louder, softer, louder, softer in a repeating pattern because of the destructive and constructive interference points. Now, if there's actual music playing, there's going to be so many fluctuations in the dynamics, louder, softer, you probably wouldn't hear very much. But let's say it's near the beginning of the partay where you first solve the problem and the DJ is just testing out the speaker with a constant frequency. With a constant frequency, if you walk in a straight line, you would absolutely hear a difference in the sound, getting softer, louder, softer, louder, softer, louder in that repeating pattern. Why do we study this? Well, that pattern is going to appear anytime there are two sources of sound, not just in this particular diffraction pattern. And if you've ever been to a concert hall, an auditorium, or some sort of other place where there's an event happening, often they have two banks of speakers, one over here, one over there, for stereo sound. And so if you have two sources of sound, you're going to get this diffraction pattern, and that means you're going to get this interference pattern where some places will have destructive interference. Now, if you're in this concert space and you paid a lot of money for your seat and you're sitting in one of these places of destructive interference, you're not going to be very happy at all because it's going to be relatively softer compared to someone just a couple seats down the line where they're hearing constructive interference. Now, if you've ever been in one of these auditoria or concert spaces, you might notice that the walls and the ceiling have like panels hanging from them or odd shapes to them. What do you think they're there for? Well, it turns out they're there to reflect the sound to these points of destructive interference. It's actually a rather complicated way to do it, but the point is they reflect the sound to those places, and it sort of evens out the sound, so every seat will pretty much hear the same thing. The people who do this have a very large task at hand to try to figure out all these points of destructive interference, and so they get paid a lot of money to use their physics to solve this problem. And that's really the moral of the story.